deliverable of a ETSAP project on modeling nuclear power in times models. And this project, it emerged because nuclear power has received a more increased attention in most countries, also among the ETSAP members. And this is in particular with this new small modular reactors that has kind of renewed the attention to nuclear power. Okay. So very first short about ETSAP. Who are we? ETSAP is the longest technology collaboration program of the International Energy Agency and it's been since 1978. And what we do is we collaborate on transparent and sophisticated modeling methodologies to model integrated energy system analysis to provide decision support for policy making. But in reality, we are a team and a very unique team of different modeling teams around the world, collaborating on developing and using the modeling framework of Markal and Times models to improve the decision making related to energy policy and the energy transition. So today's meeting is about, first I will give a short overview of the project and present the main findings of the project. Thereafter, James Glynn from ESMA will present a technology brief on nuclear power that's also a deliverable of the project. Thereafter, we are really happy that we have Young-Shu Lee here from the International Atomic Energy Agency to present their perspectives on modeling nuclear power. They are currently working on a much more extensive work on guidelines for modeling nuclear power in energy system models. And then we will go into some examples of how we have modeled and included nuclear power in times analysis, both related to data centers and including nuclear power in non-nuclear countries as Norway. And then we will have a lot of time in the end for any questions and discussions about the topic. Any questions before we start? Anything that's unclear? Let's see. So this project, as I mentioned, is a part of ETSAP project, and the results. That's a report on best modeling practices and the technology brief on nuclear power. That is a good starting point for modeling nuclear power in the energy system models. Is now uploaded on the ETSAP webpage. So you can read more details in these reports that you can find here. So a bit about the project itself. It's coordinated by Institute for Energy Technology in Norway, but it's a collaboration project with many ETSAP members, and also with IEA has been contributing with valuable inputs. So the purpose has that we are strengthening the collaboration across the ETSAP members with focus on power. We have mapped the current modeling methodologies and practices on how people actually model nuclear power in their models across different modeling teams around the world. And then we have identified key challenges and best practices. And what we have done, we have had a 2-day workshop 1 year ago. And before that workshop, we also sent in all the team members provided some inputs through a survey on how they model nuclear power and what they see as great and challenges in a survey in advance. And then the deliverables is a technology brief and a report on best modeling practices. And we are finalizing the project with this webinar here today. Just a very short background, and I'm sure most of you are familiar with this, but we see that nuclear power takes a larger and larger share of the, is becoming increasing more and more. Nuclear power is getting a part of the energy system. But what we also see is that a lot of what is currently constructed and undergoing is happening not in Europe, but in China. But most projections and scenarios, and here by the International Energy Agency, assume that we'll see a growth in nuclear power towards 2050. And here is for these 3 different scenarios, and yeah, that the IEA has. And that includes both new large-scale commercial reactors, new builds, the so-called small modular reactors, and also lifetime extension of commercial reactors. And what these small modular reactors has kind of renewed the interest also for nuclear power. And they are smaller in the way that they do not have the same capacity as the conventional nuclear power, but there are many different concepts that is that different actors are working on developing around the world with different technology solutions, cooling solutions, and so on. But in the first run, in the near term, we see that what will come as a small modular reactors will be a downscaling of the commercial nuclear power, but in the long run, it could be new technologies that emerge. And the advantage with these reactors is that they are small, meaning you can also locate them in the grid where it's easier to locate them in where there is space in the grid, for example. And they are intended to be modular or more prefabricated than the commercial nuclear power. And also, since they are smaller, maybe they can be located closer to population and it's easier to use excess heat and so on. But there is great uncertainty related to the development of this technology. What will be the winning technology in the end, and what will it cost, and so on. But there are small modular reactors under construction, and this is from Canada, where the first module of a 300 megawatt module is under construction and is planned to be operated in 2030. So now I'm done with the background, a bit about our workshop. That kind of is the basis for this project. We were 23 participants from 13 different institutes, 11 nationalities. We also have participants from the Belgian Nuclear Center and IAEA. And we worked on how do we actually model nuclear power in energy system models. And we also discussed and also found solutions for what are the key challenges and where are the solutions for us going forward. Yeah. So if you want to read details on how different teams have modeled nuclear power, I recommend you to read the reports. But what we see is that some teams model conventional nuclear power only, some teams model small modular reactors only, but we also discussed maybe it's not that different how we model these type of technologies. But what we see is that there are very different ways. The technology detail level that is incorporated in the models varies a lot between the different teams. Yeah, and also some teams mentioned that small modular reactors is just modeled the same way as conventional nuclear power, with different assumptions maybe on costs and when it can be available and so on. So in the survey, we asked, what are you doing of assumptions that have a biggest effect on your results on nuclear power? And the first on top of the list was costs. So it was a key finding that most teams find that cost is the main assumption that affects the investments in nuclear power the most. And then it was primarily investment costs because that's the larger part of the cost share. Second was the energy system configuration. So the energy system that the nuclear power will be placed in. What are the other energy opportunities in that region, country, continent? So how much nuclear power you get really depends on how much other renewables you have available. And for example, if you have stringent land use availability, that could also affect investments in nuclear power. So it really depends on the setting of this energy system. It was also mentioned that how we model operational flexibility and cogeneration of both heat and hydrogen affects the investments on third. And then it was mentioned how we include resource and material supply chains can also affect investment decisions on nuclear power. For example, water availability for cooling, or the supply of fuels, uranium, for example, or for the technology itself. And then other constraints like energy security and so on was also mentioned as important assumption that affects the investments in nuclear power. But on the top, it was costs and investment costs, and it was energy system configurations. We also, in the workshops and the report, went through that costs are different things. And we made these kind of cakes for all the different modeling teams. But what we see is that the overnight cost has the greatest share of the cost of nuclear power. But if you go to the right here, this is what is typically an input to a times model. So there are several things that can affect the cost of nuclear power in an energy system model. So you will get more inputs on the different cost components in the report. And all the teams, they acknowledge that the costs are difficult, but we also challenge them to say, okay, but just put what you have now or what you have used before. And then we compared the LCOE of the different teams. And you see it varies a lot. And this just illustrates the uncertainty of the cost. And it should be, maybe we're not comparing the same things, but it just shows that it's important to at least be transparent on the cost assumptions. And we also see there's differences in the distribution of the investment and interest during construction and the operational costs. So there are differences, but all of us, all the teams acknowledge cost is difficult, and using one cost in many cases doesn't make sense. So we identified some modeling challenges, and the first was how do we find costs? There is a large uncertainty in the cost of nuclear power. First of all, there has been built very little conventional nuclear power in Europe the last years, and for European, because a lot of these teams were European, as the workshop was in Brussels. We also have, and we don't know what will be the cost development of the small modular reactors. There's also uncertainty in policy and regulation. Maybe some countries would like to subsidize nuclear power, and then a techno-economic model maybe doesn't make sense because it's a desired option independent of the techno-economic profitability, or that you need to have policy in place to have nuclear in a country also. So there's uncertainty in policy, also uncertainty in supply chains and material needs, and that small modular reactors is not one solution. It's a lot of different concepts and solutions, and the difference between third generation and fourth generation. So it's actually more than one. It's not just to put assumptions of one solution. There's challenges of modeling operational flexibility of nuclear power, both related to how long-term energy system models are designed with a quite, where you have to have somehow coarse temporal resolution, but also the operational flexibility of fuel cycles of nuclear power was also addressed as an issue. Also, how to model and waste management and how the cost of that. And that there is, that this is related to the second point. There can be, and there is very often a misalignment between techno-economic decisions, what's optimal from a society, and what is the actual political decision making. But on the other hand, energy system models can contribute with knowledge that can contribute to provide a knowledge-based political decision-making. There's also differences between what's optimal investment from an investor perspective compared to a system perspective. And we have this challenge of discounting decommissioning costs. Because since decommissioning comes in very many years from now, in energy system model that discounts this cost of decommissioning will be marginal. So it's more a generic issue on how we should work with the discounting in this long-term perspective, if that's correct or not. Okay, so to the last slide on our ending modeling challenge, our recommendations based on this work, the best modeling practices. Address uncertainty in cost assumptions, meaning acknowledge the uncertainty of costs in communicating the results, but also it's preferable to use a sensitivity on costs to show the different outcomes. We also mentioned that maybe we shouldn't have costs, have nuclear power as a endogenous investment, but we should say what happens to the system if we invest in nuclear power, if there will be investments in nuclear power or not. But be transparent and open that the costs are uncertain. Second is to design the energy system models such that they are as technology neutral as possible. For example, if we have a 2-coarse temporal and spatial resolution, it could be that we favor renewables over nuclear. Or if we only include parts of the cost of nuclear, it could be that we, for example, if we don't include the cost of decommissioning or waste management, it could be that we favor nuclear because we haven't included all the cost over other options. So have in mind that we want to make models that provide as technology neutral results as possible, also on how they are designed. Third, account for policy, regulation, and uncertainty. And here we also recommend that we have discussed the assumptions with policymakers in the country and be transparent on the assumptions. And if there is uncertainty in the policy outcome of related to nuclear, it will also discuss it's possible to have different scenarios to show the implications of different policies. Fourth, do not treat small modular reactors as one technology. But be very precise on what you mean of what technology you are thinking about. And this is related to both how flexible they are, how large they are, but also when they can be available and what kind of cooling requirement they need and so on. So we talked about having not 80 different SMR technology, but that they can be clustered in different technology clusters related to their characteristics. Yeah. And fifth, incorporate operational flexibility, like ramping or minimum uptimes when it matters in the modeling. But we also said it's worth including it to test if it matters, such that we have a credible results related to nuclear, that we have included all the details. So it's important to include a lot of details so we have credible results also. Yes. And then in the end, I want to thank all the contributors to this project, and it's been fun. And but now I will continue, and it's a contribution. So we are coordinating it, but it's everybody is contributing here. And now I will give the word to James Glynn that will present the technology brief that is also a deliverable of this project. Are you able to share, James?
Thanks, Pernille. Can you share the slides that you just had up?
You want me to share my slides?
Yeah, the final slides after that. Thank you, contributors.
After the you.
Oh, I can share.
You sent it to me. I'm sorry. Yeah.
I'll open it here.
But while it's getting settled, is there anyone who has one question before we start?
I think there was a few in the chat, Pernille.
Yeah. Yeah, I like this comment that techno-economic models may not provide societal optimal solutions. I agree. So I think many of us working on this type of models include other type of aspects in our models, and it's often included to different degrees. For example, limitations of land and social accepted solutions and so on. Or more this life cycle aspects of producing different technologies. So it's not that we are only techno-economic in our analysis. I agree.
Can you see those slides okay, Pernille?
Yes, but not in a presenter mode yet.
Is it okay now?
Yeah, great.
Sorry. Okay, so I'll just briefly go through the second deliverable on this report, just in the space of 5 minutes. So, as part of the project, we updated what ETSAP refer to as these energy technology briefs, which are essentially a data literature review on the technology parameters required to model a specific technology. We have about 30 of them on the ETSAP website, and so we updated the nuclear power energy technology brief. So the link is there on the slides. There's about 30 pages with quite a large appendix of data. So I'm not going to get into that data right now, but I'll try and give the summary. So as Pernille said, there is huge uncertainty in the capital costs, of the overnight capital costs and the operation costs, and to a lesser degree fuel costs for different types of nuclear reactors. So when we look at the data and what's happened since the last ETEC brief in 2010, the global nuclear fleet capacity has stayed roughly the same. It's about 376 gigawatts, or let's call it 400. But where there has been shutdowns in the OECD and the West has been largely then offset by growth in Asia and largely China. So while the global fleet has stayed roughly stable, the locations where current and new reactors are is definitely shifting east. And with that shift, the knowledge and capacity to build nuclear reactors on time, on schedule, and on budget is also shifting east. Lifetime extensions are the most cost-effective mechanism for maintaining nuclear capacity or nuclear generation within OECD and within European and North American energy systems models. So the cost of a lifetime extension per kilowatt is probably an order of magnitude of 10 cheaper than new capacity per gigawatt, and so it maintains a levelized cost of electricity, at a reasonably competitive level with solar and wind. That's not the case with new capacity in OECD and Western countries. So we see this huge bifurcation, essentially, of capex costs when we look at Generation 3 large reactors from Asia and from the West, from Europe and the US. Sorry, from Europe and US. So we're seeing these massive cost overruns in Europe and US in production costs. Cost overruns and construction time rising up anywhere from 7 to 12 to 14 years in some cases, while Asian builds are being achieved on time and on schedule, probably at a quarter of the price and on time in 3 to 4 years. So this cost differential needs to be taken into account depending on what region you're modeling in your times model. While there's an awful lot of talk about small modular reactors, they're still pre-commercial. There's only one that has a contract globally in Canada, and the promise of small modular reactors is that they can remove the cost uncertainty and bring it into a factory to regularize and modularize construction. But to do that and have energy technology learning, we need an order book of 5 to 10 reactors to start bringing down those costs. One of the biggest barriers that are a concern for fourth gen reactors and small modular reactors is the fuel supply. So high assay, low enrichment uranium isn't produced in Western nations or in the OECD. It's produced in Russia and in China. And so the supply chain for fuels for SMRs is in the hands of a few countries, and that would by some be considered as energy security or geopolitical risks. We're also seeing then that electricity demand from AI and large data centers is driving this new demand for clean, firm power that is price inelastic, i.e. doesn't care too much about the cost of electricity, and is really driving interest in new reactors, or small modular reactors, and restarts of nuclear power in general, to restarts of units in the US. So there's a lot of data in the technology brief. I'd encourage you to go and have a look at it. It's geographically differentiated between North America, Europe, and Asia and the rest of the world. And it gives you some of the data here that I'm listing. So the cost of lifetime extensions, regionally differentiated capex costs, gives the lead-in construction time, which is an issue, and a binding constraint in models. It gives some details on unit commitment capabilities, so ramp rates, minimum stable levels, that's seen within historical reactor operation. And there's some details then about endogenous learning rates that are required to move from between-of-a-kind or first-of-a-kind reactors and nth-of-a-kind cost reductions. There's also some details about the needs for supply chain modeling for HALEU and the next generation of fuel supplies required for SMR and Gen 4 reactors. That's all I have. Pernille, so I'll hand the floor back to you.
Thank you very much. So if you are modeling nuclear power in any type of investment model or a long-term energy system model, I recommend you to read the technology brief. And now we'll move on to Yingshu Li from the IEA that will present how they think about the needs, how we should represent nuclear power in energy systems. Thank you. So now you had it, now it's not in presenter mode. We need to change it.
Sorry.
No, it's not easy. But you are also writing a report, right, on modeling guidelines?
Yes, indeed, we are doing that. Thanks for introducing that to the audience here. Yeah, do you see it now? Is it in
yes, now it's perfect.
Okay, yeah. Perfect. I'm just gonna. Okay, great. So so thanks very much for having me on this webinar. We are very happy to be here. Actually, some of my colleagues are also joining because they're interested in the work that you are doing. So I am from the Planning and Economic Studies section. We do modeling, we do economic analysis, we also do capacity building for countries. So part of our work is actually technology agnostic. We don't just look at nuclear, but we also look at other technologies, particularly in our capacity building work. We work with countries that do not have nuclear yet. But as our name suggests of the agency, we also focus sometimes on looking at nuclear. So I think you have already given a very good introduction on why modeling nuclear is so pertinent right now. So within the IEA, sorry, I'll have to also change the slides here. Some work that we have been doing in the last few years was we have been monitoring different scenarios. So you might be very familiar with these AR6 scenarios. So there's a database that is hosted by ETSAP. So in this database, we were able to retrieve all the AR6 scenarios that goes into the IPCC working group. So these scenarios, they are generally developed with integrated assessment models. They range from economic models to detailed global energy system models. They can be including different regions. Some of them have different sectors. They may be also looking into the interactions with land and water, and also representations of the climate system. So, and also these scenarios, these models used to produce the scenarios, they can also be quite different. Some of them are just linear programming formulations. Some of them are CGE formulations. Some of them have myopic foresight. Most of them would have perfect foresight. They can be optimization models or simulation models. They can allow for exogenous or endogenous technological changes. So we actually look at all of the scenario results that came from this database, and we were interested in looking at how nuclear is modeled. So what we found was that for nuclear, all the models actually include nuclear energy. They do represent nuclear in some form, but very few explicitly represent the advanced reactors or other applications for nuclear. So most of the models, they represent some form of generic electrolysis and electricity storage, whether this is producing hydrogen from electricity from nuclear, we don't really know. We also don't really know if nuclear is being modeled as a hydrogen, as a technology that can model hydrogen, that can produce hydrogen, sorry. In fact, out of the 1,800 scenarios, we saw that only in 80 scenarios, nuclear has hydrogen output of more than 0. The representation of the grid characteristics of these scenarios are also mixed. As you can see here, we were looking at several different aspects, grid integration of VRE, smart grids, advanced nuclear reactors, nuclear process heat, for instance. So of all of these scenarios, we saw that only 50 scenarios actually contained nuclear heat. And out of these 50 scenarios, only 41 had very small amount of nuclear heat that is being produced. So there's rather limited representation of nuclear energy technologies across the AR6 scenario models. And therefore, we actually have an initiative called the Atoms for Net Zero Initiative. So this initiative is aimed at supporting member states in evaluating nuclear's role in net zero pathways. What we do within the section and within the IEA is that we provide analytical tools, data, and benchmarks for energy system modelers. This is because we recognize that the way nuclear is represented in models can materially shape policy outcomes. This is not to say that we want to shift the way that nuclear is represented to favor nuclear. We just want nuclear to be presented in a way that is fair and that is accurate based on its technological and economic parameters. So our current work includes some meetings. So we actually have met with some of you in our in-person meetings, or we have met you online in our consultancy meetings. So these consultancy meetings bring together the modelers and IEA staff, and then we discuss specific representation problems in models. We also have technical meetings. So these are wider meetings, meetings exposed to wider group of experts, and we convene on the use of the modeling tools, and we sometimes also discuss the modeling methodology behind the results. In addition to that, we also offer direct support to modeling teams in different countries on evaluating nuclear's role, either by teaching them how to use the model or providing some form of analytical support. So far we have worked with countries like Estonia, with Singapore, with Burkina Faso, and we are also looking at some other countries that have expressed interest this year. In addition, as already mentioned, we are actually coming up with some modeling guidelines. So these modeling guidelines will contain information that's important to the modeling of nuclear energy. So we actually drew quite a lot of inspiration from our meeting with the IEA ETSAP community during the workshop, and also through our conversations with you during our meetings. So out of these meetings, maybe I can just publicize a little bit one particular meeting that may be of interest to this group. We have been organizing this for the last 3 years. It is on modeling net zero transitions, or rather modeling nuclear's contribution to the energy system. So this year we are organizing a similar workshop. It will be in Vienna. It's from the 6th to 10th of July. And currently the application portal is already open, so you may search for this event on InTouch Plus. We normally would be able to sponsor if we have budget available. So if you are interested, feel free to get in touch, or feel free to just apply directly. So during these meetings, during these workshops, what we discuss are things like the cost assumptions for nuclear, the carbon constraints, the climate constraints, the representation of VRE and energy storage, because we recognize that just representing nuclear perfectly may not be enough. In understanding nuclear's role, we also need to represent the surrounding, the energy system that surrounds nuclear power. We also discuss, say, the impact of climate change, how future weather trends can affect not just nuclear power, but also other technologies like wind and solar. And of course, we look into the modeling of heat, of hydrogen, by considering future nuclear technologies. So if this is in your interest, feel free to join us in July. It's very nice in Vienna. I'm sure some of our colleagues will tell you that. So then maybe we can move on to some of the key points or the key issues that we think are important to the modeling of nuclear power. The first is capital cost. So as our colleagues have already mentioned, capital costs can vary quite a lot between different projects, depending on the geography, depending on when it's built, depending on the design. So here I just put a chart of a few select numbers from different countries or of specific nuclear power plants that have been built recently. These numbers are illustrative only; they are not official costs. So you can look at them to look at the magnitude, but be careful if you want to use these numbers in your models. So we see that the reported costs, they vary by more than 3 times between projects. We have the Asian projects, Korea and China, being pretty affordable, or rather being pretty lower cost as compared to Hinkley Point C, which is known for its cost overruns at the moment. However, we also have to be careful when we are comparing the costs. They have to be based on the same definitions. Are we looking at overnight capital costs? Are we looking at total project costs? This has to be clear. So here the numbers, when I look up them online, some of the sources could be actually giving total project costs, and it might be unfair to compare, say, 15,000 with 2,500 in China. So the modeling pitfalls that we often encounter when we talk about capital costs and models is when we apply a single global cost without specifying where the cost is, where the projects are being built, and the status of the design, whether it's first of a kind or nth of a kind, and also by mixing the cost definitions. Are we talking about total project cost for nuclear, but are we only talking about overnight capital costs for solar and wind? So that is something that we think one needs to be rather careful about. Another thing which can be quite obvious is that discount rate is one of the key drivers on whether nuclear appears to be low cost in the model or high cost in the model. When we are talking about the LCOE basis, or when we're talking about optimization models where you impose a discounting factor. So capital intensity drives the sensitivity to discount rate, and nuclear is one of the most affected technologies here, with different discount rate assumptions. That is because nuclear is very capital cost intensive, and it takes a long time to build. So when you are looking at revenues which are accrued in the future with a higher discount rate, you will sort of squash that a lot more as compared to some of the other technologies. So at lower discount rate, nuclear is favored normally, or it is lower cost compared to some of the other options. But when we have higher discounting factors, higher discount rates, then nuclear's cost may be seen as expensive. And also another thing one needs to distinguish is between a social discount rate and a market framing of the discount rate. So I understand that quite a lot of modelers, maybe they are doing consulting projects, they are looking at forecasts, therefore they may use a discount rate that is technology specific, maybe higher for nuclear because the investors sees more risk exposure, so you impose a higher discount rate. Maybe as a social, from a social perspective, if you are a planner, then perhaps a discount rate should not be that high. So you have to make sure that the discount rate that you use is reflective of the question that you're answering and the perspective of the role that you're taking. So I will quickly go through some of the next slides. Another thing we notice related to cost and discount rate is construction time. Again, we see quite a huge spread on the construction time for different nuclear reactors in different parts of the world. We see, like, for instance, this Chinese reactor was built in 67 months. La Flamanville 3 was built over about 200 months. So this obviously feeds into your results, because you actually have to finance, you actually have to think about financing during the construction. A lot of the cost overruns are also because of delays in construction. The next thing, which the colleagues have already alluded to, is the representational flexibility of nuclear in the models. So this is actually from my colleague, Marco, who is also currently in the audience. So this is an example of a power history for one of the Swiss nuclear power plants in 2013. We have known nuclear power plants to behave in this way as baseload. They have a really flat profile. During some times, they switch off or they go through maintenance. So there might be a few weeks where they are offline. So you see a dip here. But most of the time, we think of them as being constant load, constant production. However, this is not always the case. This is more of a matter of economics rather than the nuclear's technical capability to ramp or not ramp. When we look at the French fleet, we actually see that in France, there are quite a lot of nuclear reactors. So some of the nuclear reactors would have to operate on a margin. This is a power history of a French PWR reactor over a period from 2008 to 2009, over around 1 year. And we see that, say, like a 10-day period around Christmas, so circled by this dotted line here, the nuclear power plant is actually able to do this kind of load following. So for 2/3 of the cycle of the fuel cycle, the load can fluctuate quite a lot, but in the last third of the cycle, the plant is operated in the base load mode. This is actually a restriction on the technical ability of nuclear power plant, but for the first 2/3 of the cycle, there is nothing that says nuclear power plants can't ramp, and we see the same for like German reactors, 6 E.ON nuclear power plants during 24 hours. We also see that they are able to change their production. I will just mention this part here. So we have spoken about how flexibility is a characteristic of nuclear power. It is possible by nuclear power plants to do that. Within the model, how this is represented can also have an impact on your results. So a researcher, Jenkins, in 2018, published a paper that looked at modeling of a US Eastern interconnection model. So in that model, they were actually explicitly testing how flexibility would affect the results. So for instance, if you have a mass-run nuclear power plant, that means your nuclear power plant have to produce all the time at a flat profile, then you will see a lot more renewable curtailment versus a full flexibility where your curtailment will be reduced because then your nuclear power plant can actually do some kind of variation in its production. We know this theoretically, but does this really occur in reality? Firstly, if this does occur, then nuclear power plants may have to, if nuclear power plants are always being operated as a marginal power plant, as being operated in the margin, then it might face this issue called the missing money problem. It may not be able to recover all of its costs incurred just from the energy market alone. And that is why we often talk about these out of market revenues for nuclear power. So in a model, what the model would see is that the nuclear power plant would just earn from the wholesale energy market. But actually what the plant actually earns would also include revenues from, say, the capacity market, out of market support, ancillary services. One example that is real is the auction in the US. So in capacity auctions that were cleared this year, we are looking at a clearing price for capacity at around $270 per megawatt day, and nuclear represented 20% of that cleared capacity. So nuclear actually participates quite heavily on the capacity market. And also this amount would vary from year to year quite a lot. In the previous year, the clearing price was $29. So it was like a 9 times change in 1 year. In addition to that, like even with this capacity auction, it could be that the new nuclear power plants do not recover the full LCOE from net revenues. And this was what the market monitor has found. There are also examples of other revenue streams for nuclear power plant. In the UK, there's contract for difference. In France and Korea, there's regulated rate of return. In newer developments, we are seeing that there are technology firms or these Microsoft and Amazon. They are actually doing PPAs with power plants, with power generation, in order to procure enough power for their future energy needs. So these revenue streams, they are not frequently captured in just pure optimization models with an energy only market. Okay, sorry, is it okay if I go a little bit over by about 3 minutes or quickly?
Yes, of course. I think many people think this is interesting. Continue,
great.
please.
Thanks. So another point we want to talk about when we talk about modern nuclear is obviously nuclear's application for heat production. So IEA has done quite a lot of work mapping how nuclear can produce heat, how nuclear can support industrial processes. And we see that for some of the processes which requires very high temperatures, nuclear is actually in a perfect position to be able to produce that kind of heat that's needed. So for instance, at low temperatures, of course, when you have district heating, when you have these seawater desalination, there can be a lot of alternative types of heat. But when it goes to much higher temperatures, nuclear would actually be facing fewer competition compared to other technologies. Will be able to fulfill this kind of temperature regions, say above like say 600 degrees Celsius quite easily as compared to other technologies. One thing we also discussed quite extensively during our meeting is that cost optimization may not be the only question that one should think about, that the objective of the society is not just cost, and this was also mentioned by you earlier on. So the real question is rarely, is nuclear the cheapest? Should we have nuclear at all? So we have colleagues, Rocco, who actually did some parameterization of different dimensions surrounding other aspects that policymakers would consider in addition to cost. And some of the examples where this is true in reality is the kind of phase out that we are seeing post Chernobyl, post Fukushima. The phase out is not because that nuclear is driven out cost wise, it is because there are other factors that are currently being considered. Another thing that one needs to also look at is that the inputs are not known with certainty. As we have also seen from your modeling inputs, you have quite a high range, a huge range of different costs that you put in for nuclear. That would be one type of uncertainty that we know, not just uncertainty between the models, but also uncertainty into the future. We don't really know how much things are going to cost. So we have colleagues who actually have done work related to long-term and short-term uncertainties. And also, when we look at weather patterns, there are short-term uncertainties that will affect the power market and therefore affect nuclear's role. There are a lot of other parameters that warrant attention. I will not go into them. So each of these parameters have its own modeling pitfalls. In our modeling guidelines, we are trying to describe them for treatment recommendations. So in the guidelines, which we are hoping to make ready for review by the end of this quarter, we are covering quite a lot of topics here. So you can see on the screen here, like some of the major topics that we are looking at. One which is quite important is the inclusion of energy demand. As we know, with growing energy demand from data centers, and some may say that this demand profile in the future would be flatter because data centers require more constant load, but we have also seen that there can be power surges related to the current use of non-traditional AI. So that is something that is maybe unpredictable, and we are particularly interested in including this aspect in the guidelines as well. So if you do have any inputs, we will be very happy to welcome that. So for the next steps, we have already mentioned we are looking for review by end of Q2. We are looking for publication, and we want to be able to present this during the meeting in July in Vienna. So if you are here in Vienna, maybe you will be able to see the final outputs from this work. So thank you very much. And sorry that I ran a little bit over time.
Thank you very much, Youngshu. Any questions to her presentations right away? I saw there's been some questions in the chat. Maybe you can raise your hand and ask yourself.
I could maybe answer on the lifetime part, if that's okay. Regarding the cost, I actually haven't looked into it myself, how the cost would vary if one would operate something flexibly. But for lifetime, I understand that current nuclear reactors, they are designed to be flexible. Their design lifetime is able to fulfill the kind of flexibility requirement that is required by say the EU. So you would not really expect your design lifetime to fall below, say, 60 years or 80 years if you are to operate it flexibly.
Yeah, Yunshu, if I may add some comments on flexibility,
yeah, sure.
of the plan. It is very tricky, actually. It's very difficult to quantify. And the only country that has real operational experience operating flexibly is France. And the latest results from the French operator is that basically the impact of flexibility as it is done now in the French fleet doesn't have a visible impact on O&M cost, on lifetime of the plant, and so on and so forth. Actually, this contradicts a little bit with what was said in the literature and by EDF itself in the past. So the newest result on that is that really the impact of flexibility on the economics of nuclear are on the cost of nuclear are really marginal. The reality is quite the point is it is extremely difficult to predict what would be the cost on future flexibility, because flexibility as it has been provided now by nuclear is probably much different than the flexibility that will be required in the future. So nobody can say whether having an usage that requires more ramping up and down doesn't cause cost in the future. That is impossible to say. But I would say not to have a big penalty, or not to have a penalty at all for letting nuclear to be flexible. That would be my recommendation. Taking into account, as I say, that there are a lot of things that we don't know for sure. So maybe I can just quickly add on some comments to that. So yes, indeed, the cost between Asia and Europe is because is sometimes attributed to the design, but also the fact that in Asia, for instance, in China, they have been building nuclear power plants continuously for a very long time. Whereas if you are in a country where you haven't built a nuclear power plant and you have to restart building it, then you'll have a restart premium. So even if it is not first of a kind, but because you lack the supply chain or your supply chain is not as ready, then it could be that you would face this kind of premium. So in addition, there can be differences in the labor cost, obviously. So our colleagues from Argonne National Lab in the US, they have done this net zero world study where they tried to actually look at do a study to understand the different factors affecting the costs in different geographies. So they actually have a labor cost adjustment in their projections or in their calculation for nuclear power plants. So that could also be one issue. As well, it is very complicated again, and there are many reasons. I think and I think Yunshu mentioned all of them, but regulation is also one of them. If you need to modify your design because regulator asks you for more things, that definitely adds into cost. But I would say for the time being, when you look at cost data in Western countries, so let's say in the US and in Europe, there is definitely a big factor, as Yunshu mentioned, of first of a kind impacts. And again, even if you think, for example, a Korean design exporting their design to a different countries, to a different country, the cost will be probably higher than if you build domestically. There are many reasons for that, but again, as it was said, I don't remember by Young-Shu or an earlier speaker, cost of nuclear really are extremely local, and you cannot achieve a cost of, or you cannot have a value that is valid worldwide. And this is one first fact. And the second one, there is a big difference between first of a kind and nth of a kind, and how cost will decrease if several reactors are built within a country. And it is quite challenging to say what will be the nth of a kind cost of nuclear.
Thank you so much for sharing your knowledge. Any other questions to Young-Shu or to what's been presented in the past before we move on with some examples on modeling? And you, of course, have our contact information if there's something. Now we will just go a very short deep dive into how we can model or with some examples of modeling of nuclear in times models. We will start with James Glynn, who will illustrate some analysis related to data centers and nuclear, right?
Yep, that's right, Pernille. Okay, so we're running a little bit behind time, so I'm going to try to be quick, maybe 5 to 7 minutes. So, is it working okay? So, the research question for this talk is, does nuclear have a role to play in easing hyperscale data center need for immediate 24/7 zero carbon power in Ireland? Ireland is a bit of a canary in the coal mine around data center load growth. Ireland is the headquarters for the European headquarters for a lot of large American tech firms who are already restarting nuclear reactors engaging in PPAs to restart nuclear reactors in the US. So I'm interested in exploring what is the role of nuclear in Ireland, if any. I want to look at what can we learn from the French fleet, with Marco and Young-Shu and Pernille have already mentioned. I want to endogenize the dynamics of basically the updated energy technology brief that we did as part of Pernille's project into this Irish model to explore more advanced dynamics and see what comes out of a scenario assessment. So I remember one of the technical meetings in Vienna where somebody from or the French DSO presented something similar to this slide. So this shows this day last year's unit level generation from the European electricity system operator, the transparency platform. The link is at the bottom, you can go and look at yourself. So this is stacked this day last year of all the nuclear units in France. And so the middle reactor, I won't try to mispronounce it with my non-French accent, is how we normally presume nuclear reactors to operate, flat at about 900 megawatts or 0.9 of a gigawatt. But you can see in Bugey 3 and Bugey 4, they're obviously load following solar. And you can also see in Cattenom 2, you can also see they're load following and providing other sorts of balancing services that I personally typically would have not have included in my times models 2 and 3 years ago. And this, this default assumption about non-rampability and taking historical US type availability and ramping characteristics, they are historically in the data, but they are driven by historic economics, not technical limitations. The other thing I want to say is that these two reactors on the right-hand side are modern designs, but they were built in 1987, so they're not particularly new in their level of advanced kind of rampability or capabilities. So that's just kind of a baseline. What can individual units do in the French fleet? So then looking specifically at the this is jumping around the place. Sorry, data centers in Ireland. So data centers in Ireland are consuming about 22% of electricity demand last year. It's probably the largest national share of electricity consumption by data centers globally. You see these other hotspots in Virginia around the Pentagon in the US, similarly in Paris, in Frankfurt, and increasingly in Tokyo and Beijing. But they're putting they're already large and they're growing at a significant rate, about 6% electricity demand growth year on year in Ireland, and that's outstripping the ability for new wind and solar to provide new generation and to reduce the carbon intensity on the grid. So I'm curious to see, are there other technology options that can help and decarbonize the grid? This is showing the projected electricity growth by sector in Ireland. So our current electricity demand is about 35 terawatt hours. You can see that residential, commercial and industrial sectors are largely flat and projected to stay largely flat even with economic growth and population growth. The electric vehicles and heat pumps are projected to grow over the next decade, but the majority of the growth in a medium scenario is this orange on top, which is large data centers within about 15 to 20 kilometers of the city centre in Dublin, which causes huge congestion on the transmission grid and a huge need for growth in electricity generation. So I wanted to try to model this more accurately than I have done in the past, and that is typically done. So I built this unit level times model. So it's the whole island of Ireland, the Republic and the north of Ireland. It takes each individual geolocated power plant, each individual wind turbine, each individual solar farm. It takes the technology stock from the TSO and the DSO. It takes the future energy technology menus from the National Renewable Energy Lab in the Rockies in the US and the Energy Information Administration in the US, and currently integrating the Danish Energy Agency catalogues, and then calibrated the operational constraints for nuclear as per the new energy technology brief from the ETSAP project. The demands are from the air grid, the DSOs, kind of short-term projections, and then the long-term were derived from SSPs narratives, and then the operation of wind and solar is based on weather reanalysis in the short term and climate adjusted Earth systems models for the future. So very briefly, and Prina, tell me if we're maybe 2 or 3 more minutes. So typically we haven't really included operational unit commitments in times models. So just very, very briefly, I've included nuclear reactor unit commitment ramp rates and cycle rates as best I can, following this updated data from the energy technology brief, but I haven't included that ramp rate and minimum stable levels as a function of the fuel cycle that Yanshu mentioned earlier. So merging unit commitments and dispatch modeling into times type modeling is what I'm exploring here just for the power sector. The other thing I would say, and I've said it quite a few times in these closed meetings, is that our time resolution and our time resolution really matters to how we capture the variability from renewables for many different reasons. But within times models, given that we're not just modeling power, we're modeling all sectors, the whole system, when we start to go to hourly and 15-minute resolution, you can create models that are in the order of 200 gigabytes to a terabyte of RAM, and it just becomes nearly impossible to solve. So being very careful about creating your time structure is something that I've talked about before, and again, I have this hybrid time structure where I'm trying to capture the moments and the minutes and hours and weeks of maximum stress on the Irish grid. So maximum demand, maximum generation, maximum wind generation, maximum solar, and then the lowest generation weeks, so the Dunkelflaute for wind and solar, and replicate that going forward. So then the scenarios that we ran is not just 2 or 3 scenarios, it's looking at different time resolutions with unit commitment, with discrete new capacities turned on and off, with construction lead times turned on and off, with critical mineral supply chains turned on and off, forcing nuclear on and off, and then having electricity demand ramping or growing faster because of data centers. So the short end of it is, when I'm trying to give nuclear as much of a reason to come onto the Irish grid as possible, we still don't see it coming into the Irish mix yet, unless we force it on and say you have to have a minimum 400 megawatt SMR. We need more uncertainty analysis to find the causality of this outcome. The technology options that we're giving the model, it doesn't have co-production for heat or hydrogen in this model, and we don't have local distribution constraints. So that's another reason to think that it might be underestimating variable renewable curtailment. I want to split out the demand to see, can we force data centers to have zero carbon 24/7 power. That's another constraint that they need to be looking at anyway, and then that might change some of those results. So Pernille, I'll stop there because I know we're running a little bit out of time, but that's
Thank you.
a brief overview.
Thank you for the presentation. Any questions to James before we move on? Stian?
Yes, thank you for an interesting presentation. You might have said it, but with reference to the rest of this workshop, what cost level did you assume in these different scenarios?
So I'm taking the EIA and so the American Energy Information Administration capacity cost, so it's about $6,600 per kilowatt, and then there's 2 different technology options from NREL that were in the 5,000 to 7,000 per kilowatt hour in the short term, and then they both declined to about 4,500 dollars per kilowatt by 2045.
And still you don't see it pop in without forcing it into the mix?
No.
Okay, interesting. Thank you.
Okay.
Any other comments or inputs? I will be quite fast on how we have modeled nuclear power in Norway before we have some time. Do you see my presentation in the right mode now?
Yes.
Yes, well, that is it. I will skip it, but we have used our Norwegian times model, and Norway is a country with not any nuclear, but the nuclear power is very high on the political agenda. So we have to include it in our analysis to be relevant as researchers. But I will just skip what we did. We did sensitivity because we ended up with what should we use of investment cost in this analysis. And if you look at cost of investment cost of nuclear power, we could see kind of conventional nuclear to be around 6,000, but that's the Norwegian authorities. They reported to be 14,000. But we also recently had a governmental report, or a report, what should I say, ordered by the government to say about the role about nuclear in Norway. And this report had the cost of nuclear power ranging from, or the small modular reactors, from 11,000 to 18,000. But also here we need to have in mind there's a difference between first of a kind and end of a kind, because here it's a 2040, 2050 perspective. So we did a sensitivity analysis on ranging the investment cost from 6,000 to 14,000, just because it's easier for us. So we don't have to make a, yeah. But this is the investments in nuclear power in the different Norwegian regions, dependent on the investment cost, but also the demand. Because we had two different demand projections. And of course, the possible role of nuclear power depends on future demand. And we see that some regions are more profitable than other regions. This is the region, the NO1, that's with highly populated. And NO2 has a lot of flexibility with a lot of hydropower, but also with a lot of transmission capacity to Europe. But what we see is also the investments in, it's not any surprise, depends on the investment cost. And if we have a low cost that we assume here, we can get approximately 15 modules of 300 megawatt SMRs with a medium demand and 30 modules with a high demand. So this is for us maybe what is a indication on what is the maximal potential of nuclear in the Norwegian energy system towards 2050. But what we also saw is that this is a linear model, but if we didn't consider if we get very little nuclear power to be realistic solution, because everything around needs to facilitate for one SMR module. You need the waste management, you need competence in place, you need the security aspects in place, you need to have the policy, the regulation, and everything. So it's also a question about what is the minimum amount that we need before the society thinks nuclear power is a reasonable solution. So this is, I think, something we should, I hope somebody will work on in the coming years. What is the minimum amount? And I've heard it's around 10 modules, but maybe some of you have some other perspectives. So this is how we dealt with the uncertainty in investment costs. But we also used this analysis to show what is the competition between nuclear power and other renewables. This is investments in electricity generation with 6,000 euro per kilowatt, 7,000, 8,000, and you see the nuclear here in orange. So there's also no surprise, but if we get nuclear power in the system, it competes with the most expensive technology, that is in Norway, offshore wind, and particular floating offshore wind. So there's a competition between the most expensive technologies. So if we get nuclear power, we can see that it can influence the investments in offshore wind. Followed by solar. In Norway, doesn't have the best solar conditions. And also by some hydropower upgrades. But what we see is that onshore wind, it will not influence the investments in onshore wind, because Norway has really good wind conditions, and it will be the least cost solution, independent on the range of investment cost of nuclear power. So this is how we dealt with it here. I'm not sure how we should deal with it next time, but it's just to show that we can illustrate the effect of different investment costs. So that was what we had on the agenda. Any comments or inputs or questions? Anyone who wants to share anything? We are open. But I like what has been mentioned here earlier, that the nuclear power is complicated. So it means that we need to work on this together. So I see maybe a hand, Matthias.
Yes, hi. Thank you a lot for the presentations. Can you elaborate on what you discussed with respect to the uncertainty analysis? Because it seems to me that including forecast errors or balancing markers is something that's a system cost contribution that is very tricky to account properly for in planning or capacity expansion modeling.
Yes. We have some modeling teams in the ETSAP community that includes these markets explicitly in the models. And we have some teams that doesn't. But you saw on the presentation of Yungshu that the income is significant in these markets. So it would be really interesting if more people could see if including not more than energy markets will affect investments in nuclear. I'm not sure if I answered your question.
Yeah, surely, yeah. Good point,
Yeah.
thanks.
Yeah.
Yeah, first of all, thank you all of the speakers and contributions here for very interesting presentations and insightful slides. I was wondering, given sort of the headline here in the topic and this group of very knowledgeable people, if there are any plans of having a written sort of synthesis that will be published, that will have best practices for modeling nuclear power in long-term energy system models, or if it will be this webinar recorded.
So you believe it can be turned into a paper? It has enough.
I think it would be at least very useful to have a document that sort of points to some of these insights in a shared setting where, because there seems to be a lot of overlap, I think, in terms of the main inputs and insights. It could be useful for not just the people present here, but for a broader community of energy system modelers.
I agree. I think we should discuss it internally in the group, and who will take the lead? James?
Just to clarify, I don't know if Stian, you missed the start of the webinar, but there is the output report from Pernille's workshops on modeling best practices. The energy data technology brief is on the ETSAP website, and the IEA are also publishing their modeling best practice. Is that what you mean, or do you mean something else?
No, that's a good reminder. Thank you. Yeah, this is more or less what I mean. It's mostly to have a place to refer to, and for example, on this insight regarding flexibility on nuclear power and its ability to ramp, which sometimes is discussed, to have a place to refer to. But if that already exists, then
yeah.
Yeah, I think both reports are on the ETSAP website, and there's a lot more detail in those reports and citations than we had time to refer to today.
Yeah, but I also agree a scientific paper could broaden the audience even more. Vion? I guess I'm not. Yeah. Michael,
you pronounced it right.
Please.
Yeah, I just wanted to ask about the flexibility issues. Like, are there any operational issues while operating nuclear power plants in flexible mode? I mean, quick ramp up, ramp down mode.
I think we answered this question earlier, or Marco and Yungshu did. Or do you have anything to add?
Do you mean like maybe like starting and stopping the nuclear power plant, or do you just mean the ramping aspect?
Ramping aspects of operating at lower loads, below the technical minimum.
Sorry, you're a bit soft. Could you, like, I didn't catch that. Could you repeat that, please?
Sure. So I meant to ask below the technical minimum or at lower loads at around 40 to 50% of the load. Are there any operational issues while operating it in such flexible mode?
Right. So according to at least the European utility requirements, the nuclear power plants are designed to be able to operate at least for extended periods at low power, at least at 20 to 40%. So is that the kind of level that you're talking about? So they should be designed to be able to do that.
Okay, thank you. That helps.
And then, Michael, the last comment or inputs is from you.
Yeah, it's not really a comment, it's just a reminder. You asked from some material about nuclear flexibility, and there are two excellent reports, one from the Nuclear Energy Agency and one which is probably my recommendation from the IEA on nuclear flexibility. You can Google them. Don't have the title with me, but you can Google it and you can find a lot of technical information on what are the potential of nuclear in terms of flexibility.
Yeah, thank you very much for pointing it out. And then I will end this meeting. I want to thank you for participating and being interested in our work. And also I want to thank James and Yingshu for your contributions and all the partners of this project. So thank you.
Thank you.
Thank you.
Bye-bye.
Bye.
Thanks, Pino. Thanks, Nishi. See you.
Thank you.
Thank you.